declare a variable named A and store the value 3 into it. Declare a variable named B and store the value of A multiplied, I'm just going to say times, sounds childish, times 10 into it. And then write a loop of any kind. And by the way, I mean in any language. I don't care whether you write this in assembler or whatever. Just don't write a whole class. Don't make it complicated at all. This ought to be like 5 lines of code. 5 or 6 or 7. Write a loop that prints hello 10 times in the language of your choice. And then write a command that asks the user for their name and stores the result in a variable named FN. N. Good enough. All right. Maybe capital N since our other variables were capital letters. All right. That's enough. If you can't do it, just put can't do it and upload it. I'm not going to kick you out of the class. But I expect that majority of y'all will be able to do this. And I'm not going to paste it into a compiler and make sure it works or whatever. All right, so the first thing I want to talk about, well, I'm just going to kind of throw the Wayback Machine on, and we're going to look at what an old computer might have looked like. So this is the Harvard Mark II. I'm sure that they started the design of this during World War II. What the Americans tended to do was build computers to help with weapons, and the English tended to build computers to try to crack the codes. So they had slightly different design goals. But maybe I should have done Harvard Mark I. They did not work the same way. Even that one's too modern. I don't want anything that new looking. Let's look up ENIAC. All right, here we're going. Now we're cooking. Well, thanks for the blurry picture. I'm not going to take long looking for it. If you eyeball what's going on here, they program these things using patch cables, essentially. And the data, even before this, there were primitive calculating devices, right? There were calculators dating back to the 1800s, you know, in some form of mechanical calculators dating even further back than that, you know, and then you had abacuses with the things that you could select. But the digits, the numbers, were stored on vacuum tubes. And vacuum tubes, you know, were just light bulbs. They were either on or they were off. Kind of symbolize a 0 or a 1 that way. And later on, people came up with the idea of saving data, and this sounds ridiculous, on a cathode ray tube, like your TV. And if there was a dot on the cathode ray tube in a certain place, that was a 1. And if that spot was a 0, it was a blank. And then if you ever turned the cathode ray tube off, you lost your data, just like with a vacuum tube. So they really did not have vast quantities of memory available to them. They didn't have solid state. They didn't have RAM or anything like that. And the question was, how do you store information in one of these things? Now, nowadays we have all these standards. You know, the IEEE standard for storing an integer in a computer, you know, and it specifies that it's going to be a certain number of bits wide and how the data is going to be encoded and how you put a negative number into it. They were making all that up as they went along. They didn't have ASCII and, you know, standards for what integers and floating points. So I'm just going to demonstrate first the counting system known as binary. I know that y'all who have sat through my fundamentals class have already heard this lecture. I'm going to only give an abbreviated version of it. But if you were in a car and you were driving along, each mile marker, it increases the digit, right? Until you get to 9 miles. Then you get the exciting rollover, which is where this resets back to being the minimum value of the counting system, and then the next column is incremented by 1. So since in decimal your digits are 0 through 9, when you increment that 0 again, you can't increment it anymore. 9 is the maximum value, so it gets reset back to 0, and then the next column is incremented, and so on, right? I mean, we know that, just when we were learning counting as kindergartners, or whenever you learned to count past 10, you kind of got the idea of that one. Well, what if there was another style? Well, this is known as base 10. Decimal, deca, 10. You could have what's known as octal. That's base 8. We're not going to talk about octal except just to mention this. It was actually commonly used at one time. 0, 1, 2, 3, 4, 5, 6, 7. Whoops. Well, octal only has 8 digits, so you could count 0, 1, 2, 3, 4, 5, 6, 7. Those are 8 digits. Notice this zero-based indexing that I mentioned previously. If we were computers, anytime you asked somebody to count, we would, instead of going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I guess we'd have this extra finger left over, but that one would have been dedicated to being 0. So our automobile that drove in octal land, once we hit 7 and we wanted to go another mile, that one would reset back to 0, the lowest digit in the counting system, and we would increment the next column by 1. Well, that's well and good, but computer memory is just on and off. Even before vacuum tubes, they had mechanical relays. Mechanical relays could, if it's closed, you have current going through it. And if it's not closed, you had no current flowing through it. Now, there were other kinds of calculating devices, which were gears, and each position on the gear meant something else, but that wasn't really an electronic computer. That was, So we're going to deal with a counting system that only has 2 digits, base 2, also known as binary. And so we only have 2 digits. So we hop in our car, we drive 1 mile, and then we drive another. Whoops, we've already maxed out our counting system. So we reset that one to its lowest value. We go another mile. Well, 0 easily increases to 1, no problem. Now we go another mile. Well, this one sets back to 0, meaning that we have to increment this one, but that one's already maxed out, so we have to increment this one, and so on. So that's a counting system using binary. Did it have to be like that? Well, I mean, yeah, a pure counting system, you pretty much would increment the numbers like that. But did they have to be stored like that inside of RAM? Well, it makes sense now that it's already, 40, 60, 70, 80, years of precedence, that, the bits correspond to the numbers like this. If we kept counting, I'm not going to keep. All right, so these are the values, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Why am I not using the tab key to make things faster? All right, and then if we were going to keep counting, we add an extra place. And then if we were going to keep counting still, we would add another place. And if we were going to keep counting still, you can kind of see what's going on here. 32, what's the next one going to be? Yeah, 64, and then 128. And then 1 followed by 8 zeros is 256. And so on. Okay, so if we had the number, I'm just going to pick one, 79. I don't know what that is in binary. I'm going to try to figure it out. There's more than one way to convert from decimal to binary. One way is just to go, okay, how many 64s could I fit into it? I could fit one 64 in, and 79 minus 64 is 15. That's kind of, it works, but there's an algorithmic way as well, which is where you just keep dividing by 2. 79 divided by 2, and I'm not going to ask you to do this conversion. 79 divided by 2 is 39 with a remainder of 1. And so 39 divided by 2 is 19 with a remainder of 1. And 19 divided by 2 is 9. This is interesting, with a remainder of 1. 9 divided by 2, when is it going to... Did I pick a number that was all ones? That was not my goal.
No, you didn't.
All right. So 9 divided by 2 is 4. Okay, good. I finally have an even one with a remainder of 1. 4 divided by 2 is what? It's 2 with a remainder of what? 0. 2 divided by 2 is 1 with a remainder of 0. And 1 divided by 2 is 0 with a remainder of 1. And then when you actually write your number, you write it from bottom up. So it's 1, 0, 0, 1, 1, 1, 1. Now that's 7 bits. And by convention, hardware designers have decided that 8 bits is the smallest amount of memory that a computer will access, called a byte. So I'm going to fluff this up to make it 8 bits. So this number, if I got it right, is equal to 79. Now I could cheat. If I give you homework on this, I don't want you to cheat, but you can check your answers. So 79 in binary is 1. Yeah, I think I got it right. Yep. All right. Miracle of miracles. Got it right. Okay. So if your program calculated that somebody's age was 79 and it was written to memory, then it may be stored like that. But that wasn't the first way that data was actually stored in computers. They use something called binary coded decimal. What binary coded decimal is each decimal, each place gets its own chunk of bits. Using the same chart, I didn't do 9. We would want to do 9 as well so that we would have every digit in the decimal system. And I am going to fluff these up to 4. Engineers love powers of 2. In dealing with computers, on and off, that's 2 states. Okay, so here we have 10 different values represented as bits. Well, if I go down here and, well, I guess I'm going to put it above it because I want to keep it on the same page as this. But if I was going to represent 79 in BCD, which stands for binary coded decimal, I just do a straight lookup. Well, what's a 7? A 7 is an 01, whoopsie. A 7 is an 0111. Now what's a 9? A 9 is a 1001. That's a completely different result from what we got here. Every digit in binary coded decimal occupies 4 bits. And somebody decided that if 8 bits is a byte, 4 bits is a nibble. So every digit in binary coded decimal is represented by 4 bits, with dramatically different results. If we had the number 255, and I'm not going to do the calculation because I happen to know what this is. 255 represented as a binary value is just all ones. 255 in BCD is, well, a 2 is 0001, and a 5 is 0101, and then another 5 is 0101. Completely different. For one thing, notice that this is shorter, right? This is 8 bits, and this is 12. And the efficiency continues to decrease as the numbers get larger in BCD, in binary coded decimal. And this is the way that made sense to the engineers in the 40s and the programmers in the 40s and the 50s and the 60s and like the IBM engineers who invented the System 360 or whatever. There's lots of applications out there that still write data out to memory in the form of BCD. It doesn't mean they're stupid or anything. It just means that that's the way that the engineers chose to do it. And then later on, engineers designed the computers instead to just store as pure binary rather than as BCD. And there's another question of how to save data. Well, ultimately, everything is just numbers to a computer. And even underneath that, everything is just zeros and ones. So if you have the word, hello, it's stored in your RAM and ultimately to your disk or your flash memory as a series of digits. But before we get there, I want to talk about hexadecimal. Hexadecimal is a representation where you, hex meaning 6, decimal meaning 10, so there's a total of 16 digits in it. Not only do you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, you've got letters as well. A, B, C, D, E, and F. Why did they stop at F? Because that's enough to represent 16. If you're a Russian engineer, did you use English letters A through F? No. You use, whatever the first 6 letters of the Russian alphabet are. But nowadays, everybody uses A through F just because, computers all standardized. It always kind of interests me, the idea of somebody, a programmer who, grew up in, Korea or whatever, and then they're learning a language, and all the verbs in the computer, language are probably written in English, and so you're learning, not only programming in a different language, but that language is written in a different language as well. It's just kind of a weird idea to me, open and close and stuff like that. Nowadays, a lot of programming languages allow you to use more than just ASCII characters to write your program. So you might be able to write functions, that same word in different languages. But anyways, so hexadecimal is a way of encoding or a way of representing these underlying bits in a different scheme rather than as decimal numbers. So if we were going to, let's go back to talking about decimal though. If we're going to convert binary to decimal, we just do some simple adding. If we have all these different places, that's the ones place, that's the twos place, that's the fours place, and that's the eights place. Because this is 2 to the power of 0, that's 2 to the power of 1, that's 2 to the power of 2, and that's 2 to the power of 3. This is 2 to the power of 4, which is why it's 16. This is 2 to the power of 5, if I spaced them all out, right, with up to 8 digits. 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, and 2 to the power of 8. I think I've got that off one. This is 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. Why to the power of? Because just like when you're counting in decimal, these are tens. 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, right? So you have hundreds and tens and ones, and then going the other way, you have thousands and 10,000s or whatever. So binary works the same way, where that's the least digit, and then as you keep going on, it's, 2 to another power of 2, or easy to think of it as just doubling each time. So, if we have 8 and 4 and 2 and 1, heck, let's throw 16 in there. If we have this number, I'm going to space it out like that. This means 1 times 2 to the power of whatever. I'm going to write their powers above it, but that's almost just going to confuse things. So this is 2 to the power of 0, right? This is 2 to the power of 1. That's 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. So the representation of this binary value is 0 times 2 to the power of 4, and I'm going to write it out in long form, but this is the only time I'm going to do it. 0 times 2 to the power of 4 plus 1 times 2 to the power of what? 3 plus 0 to the times, yeah, this is tedious, times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. All right, thank goodness I'm done with that. I don't want to do that again. Or I could write it like this, right? Equals 1 times 2 to the power of 3, which is just 8, plus 1 times 2 to the power of 2,
2 to the power of 1.
which is, yeah, 2 to the power of 1, which is 2. All right, and then obviously that adds up to 10. And if we went back up here to when we had our odometer, yeah, I didn't even get to 10, did I? But if we kept going, that's a 10. I'm going to go ahead and go out to 16, 15 anyways. Maybe you see why they chose hexadecimal. There are 16 different possible values that can be stored in 4 bits. So by using hexadecimal representation, we're using 1 character to represent 4 bits cleanly. You don't have that kind of one-to-one relationship between digits and bits if you're talking about binary versus decimal. You did in BCD, but we kind of saw that BCD is a little bit less efficient because it takes more bytes, more bits to encode BCD. So that was a long form conversion of that. But I'm going to do another one. What's the first digit? It's a 16. So I have a 16 there. Do I have any 8s? No. Do I have any 4s? Yep. Do I have any 2s?
Yes.
And what's that add up to? 22. So that's converting binary to decimal. I already showed you how to convert decimal to binary. I'm not going to ask you to do it. It's that algorithm where you keep dividing by 2. Converting binary to hex. Well, you could do the same thing that we did here, right? And then we could just, no, we're not going to do that. Instead, we're going to create a binary to hex chart, which is just this thing right here. But I'm going to add letters going down it. And the letters represent the digits larger than 9. An A is a 10, a B is 11, a C is a 12, a D is a 13, right? So I'm going to paste this again. But I'm going to actually replace that 10 with an A. Good luck trying to write this down as fast as I copy and paste if you're writing notes by hand. There we go. So let's say I have a sequence of binary digits. All right, I just arbitrarily made that up. Easy way to convert it is just to do a simple lookup. What's in 0101? I scroll up here. Well, the first thing I'm going to do is I'm going to break these into clusters of 4. And I'm going to start at the end just to make sure that I hit a perfect boundary, because maybe I typed 13 zeros, digits rather than 12 or something. Okay, so I'm going to go back and space it up like that. All right, what is an 0101 according to my little lookup chart? Yeah, that's a 5. And what's this? Yeah, so you see exactly, whoopsie. You see exactly what I'm doing there. What is that one? That's a 7. I mean, and yeah, we could convert these into our head, or maybe you get them memorized, but if you have this table in front of you, this becomes, remarkably fast. You can do it in seconds. 1100, what's that? C. It's another C. What do you know? Alrighty, and that is a 1. Okay, so this number in binary is equal to this number in hex. If you feel like doing the opposite, it's still just another lookup. So I'm going to make a hexadecimal string of digits. Hexadecimal being, 0 through 9 plus some letters. I'm going to just put a word in there, so, 0, 9, cab, whatever, and then 72. It's a reverse lookup. 0 is 4 zeros. What's a 9? It's a 1001. What's a C? We keep using that for some reason. Yeah, 1100. What's an A?
1010.
And a B, 1011. And a 7, 0111, and a 2. Right, okay, so I converted that hex to binary using the lookup table. And here I'm going to convert that binary to hex using the lookup table. Alrighty. Before I talk about ASCII, I just want to burn this into your brains a little bit. I have a worksheet here that I would like for y'all to open and to fill out. That's the binary hex and ASCII worksheet. Let me make sure it's available to you. When did I set it to be available? At 7:20. Right, okay. So, just go ahead and download it.
Okay, I think the date's wrong. It's a week away.
Okay, you have to wait till next week to do it. No, why don't I fix that? Yeah, what do you know? Why don't I remove the restrictions entirely? That's the fastest way to solve it. All right, now you can get into it. So what I'm going to do is I'm going to download it. I'm going to save it to somewhere easy to find because I want y'all to upload it. This is going to count as a homework grade, but we're going to do it in class, but you do get some homework credit for it. Alrighty, binary to decimal. Go ahead and convert these 6 binary sequences to decimal. And having the powers of 2 nearby is handy, so I'm going to go ahead and just put them out there. Oh, come on. 128, 64, 32, 16, 8, 4, 2, 1.
Why did you do so many of them, Professor?
I don't know. I was ambitious. And originally planning on making you do this as homework, where you have all the time in the world. You don't have any other lives. So this one here, 01011. Somebody help me out on that one. What are those digits? Right, so that's an 8 plus a 2 plus 1. Because we're using 5 digits there. Whoops, that's 6. 5 there, so it's the 8 plus the 2 plus the 1. Don't skip to the next section, even though you probably know how to do it, because if you continue typing, I'm going to assume that you're still working on this one. Try and give everybody just about enough time to finish it. I changed my mind. Feel free to fill in the seconds. Yeah, Daniel's gone crazy. He's already got the whole thing done. All 3 sections. I think we're about done. We've got a mark. No, getting there. Yeah, so that's 256. Excuse me, 128 plus. if you ever have more than 4, you just keep, doubling them each time. So that's a 128. All right, so I'm going to do the last one so I feel like I'm almost as smart as y'all. 128 plus, what are the last 2 digits? 2 plus 1. All right. And if we set them all to 1 and we added them up, it'd be 128 plus 64 plus 32 and so on. That'd be 255. And there's a formula for calculating the largest value that can be stored in a number of bits. And that formula is 2 to the power of n minus 1 is the largest value that can be stored in that number of bits. So if you have 8, it's 2 to the power of 8 minus 1, which is 256 minus 1. All right, the next one, I just want you to count from 0 to F. I kind of wish I hadn't goofed that little border there. In binary, just like our binary odometer. So if a 4 is a 0, 1, 0, 0, then a 5 is an 0, 1, 0, 1. What's a 6?
0110.
Yep. 0, 1, 1, 0. 0, 1, 1, 1. What's an 8? Yeah. 1, 0, 0, 0, which makes that a 1, 0, 0, 1. So what's an A? Well, we just keep driving our odometer up. 1, 0, 1, 0. 1, 0, 1, 1. 1, 0, nope. 1, 1, 0, 0. Have I messed this up? 1, 1, 0, 1. No, I think I got it right. Okie doke. So once you have that chart filled out, it's easy to do the next one. Converting hex to binary, just like I showed you. You just do a simple lookup. To convert this 0F04, well, a 0 is 4 zeros, and an F is 4 ones. Another 0 is 4 more zeros, and a 4 is an 0100. So I just, looked up each hexadecimal digit and wrote its binary equivalent. Okay, so ASCII to hex, we have text, we have words, people's names and addresses and stuff like that. Those are not numbers, but they have to be converted to numbers in order to be stored. And pretty much the world has settled on, or had settled on, ASCII. Nowadays, people have settled upon Unicode, which is a superset of ASCII. ASCII is an 8-bit character set. It's actually 7. Remember when I said with 8 bits you could hold 256 characters, up to 255, largest value? 7 bits would hold up 127 different values, which is pretty much enough for everything on the keyboard. Uppercase A's, lowercase A's, and digits and punctuation, and plus some control characters. 6 bits is enough to store punctuation and uppercase letters only. 5 bits, I'm not sure that you could store the complete, typewriter keyboard in 5 bits. Maybe you could. 2 to the power of 5 is, 32. That's not enough to hold, the English language. So, you have to pick some way, and I know that some of y'all know that ASCII is not the only way to do it. There's also something known as ASCII. And these things are arbitrary, if I was going to write, a way of storing text as numbers, I might say, okay, an A is a 1, a B is a 2, a C is a 3, a D, all the way up to Z is a 26. And then maybe lowercase a's, a lowercase a is a 27 and a lowercase b is a 28. Well, that would work. And then maybe I could put some punctuation past that. And, well, that's not how they chose it. EBCDIC is essentially an IBM invented format, and since IBM was the 8,000-pound gorilla in the business, it wound up being remarkably popular. But then there was an alternate format. EBCDIC has some quirks in it, such as the letters are not completely contiguous in their representation. Meaning, well, let's see if we can find an EBCDIC chart. Can't find one that represents it in the way that I want remarkably quickly, I'm going to stop looking. Oh, really? Yeah. You could trust me that you get, as you're counting A, B, C, D, E, F, G, H, I, J, K, you wind up at a discontinuity point where there are suddenly some other things before you keep going down the alphabet. It doesn't make it bad. You could have sorted these into a random order. It's a completely arbitrary choice. But the folks who decided to come up with an alternate system other than EBCDIC came up with the ASCII table. And what they decided is that everything less than the value of 32, meaning everything that could be stored within 5 bits, were control characters. What kind of control characters? Well, like, imagine teletype machines. You have two machines that need to communicate to each other over a telephone line. And so when one of them sent the digit 7 down the telephone line, it would ring the bell on the other machine. And then one of them sent an 8, it would do a backspace. And if one of them sent a 9 to the other one, that machine would do a tab, and so on. Shift in and shift out. You press the shift key, it might generate a 15. Notice also this hexadecimal column. And then there's all these, start of transmissions and end of transmissions and, acknowledgement of and vertical tabs. Well, we don't even think about vertical tabs anymore, but if you had that, the scrolling printouts, with the little perforated edges and stuff like that, maybe a vertical tab, is useful. So the first 32 different possible values were for control characters. And then they decided that the next 32 were going to be punctuation. So space and so on all the way up to a slash. And then, let's go ahead and throw the digits in, and then let's go ahead and throw some more punctuation in. Again, these are completely arbitrary choices, right? The numbers could have been first, followed by the rest of the punctuation. Or maybe all the punctuation would be contiguous, and then the numbers would be the last 10, whatever. And then we went over here and we got the letters, A through Z. These were the hexadecimal values, 65 to, 87. I think that would be enough that you could do that in 6 bits. I could be wrong. Maybe that requires 7 bits. Not sure about that. So that was great when you only had screens or, teletype, needed only send uppercase letters. They didn't care. So, but then you're going to store lowercase. They tacked on another bit to the standard. And so the difference between an uppercase and a lowercase is that you just effectively add 32 to the value. And if you have a D, which is a 68, then if you add 32 to it, you get the lowercase version of the letter. So every time you depress a key on your keyboard, it's sending some combination of bits down that USB cable to your computer so that it can be stored in RAM as a series of digits. And this is just one form, but it's the most common form, or it was the most common form until a superset was created. And why would you need a superset of this? Well, I don't see any German characters on here. I don't see any Russian symbols. I don't see Korean and, you know, the various flavors of Japanese and, you know, and Swahili and, you know, Urdu and, you know, there's thousands upon thousands of languages, Elvish and Orcish and, okay, I'm not sure that those are in there. It would not surprise me if a Klingon had been put in there or not. So,
Look that up. It's the Klingon version of ASCII.
yeah, let's look at that up. Klingon, but it's not going to be ASCII. It's going to be the next series, right? Because there's way too many to fit in 255. Let's see if Klingon was ever suggested as Unicode. Klingon alphabets. It has been proposed.
Also, they're not that
Yeah. So anyways, what Unicode is it's what's known as an extended character set, where you use more than 8 bits to store. You know, when it was first invented, it was 16. And then people decided that maybe even 16 bits wasn't enough. But, you know, how many different characters could you, different values could 16 bits hold? 2 to the power of, yeah, that was supposed to be to the power of, not times. Okay, so 65,000 different letters seems like a lot. But then you start adding emoji, you know, and they keep coming up, you know, with more emojis so that your phone can, you know, send sad faces in 5 different flesh tones plus orange and, you know, and green and blue and whatever. So, yeah, extended character sets. We're not going to bother with those. Just know that the first 127 places in the Unicode table match the ASCII chart. They kind of, you know, grandfathered those into the larger format. So when you edit a text document now on a computer, if it's a simple text editor like Notepad or, you know, a C text editor or a Java text editor or a programming text editor, it's probably saving its data in ASCII anymore, if you're using this kind of system. You know, if you're using, you know, IBM mainframe or something like that, even those tend to run Linux and stuff like that anymore, so they're probably saving there. But, you know, I can't act like I know that much about it. But if you're using Word or anything else, it's probably being saved as Unicode instead. So when you compose an email to somebody, it may be saved as ASCII and transmitted to them as ASCII, but it may be transmitted to them as Unicode so that, you know, somebody can insert Arabic or, you know, Farsi characters or whatever in it. So if we wanted to save some text, if we sit there on our typewriter and we type for a while, and those digits would be sent down the cable and stored in your computer's RAM as numbers, we would use an ASCII table to look that up. Or we could totally cheat and use, you know, a conversion program to do it. I'll show you one of those, but I don't want you to use a conversion program if I ask a question, you know, on a quiz or whatever. I want you to prove that you know it. So let's say that I have the word apple. How about red apple, so we have a space in it? Okay, again, I just do a lookup. I go to an ASCII chart, and the easiest one for me to ever find is just ASCIItable.com. It's hard to believe that somebody's putting in, you know, paying for a website to put up the ASCII table out there. I don't know, you know, unless it gets some advertising out of the corner or stuff like that. Yeah, cheap perfume. That's how they pay it. They're hoping that the people who look up ASCII tables are also interested in cheap perfume. Well, anyways, we had red apple. So what I would do is I would find a capital R, and if I was saving these as decimal digits, then I would write down, okay, that's an 82. But instead, I'm going to write down the hexadecimal version of it. So let's see if I can get all of this on the screen at the same time. Red apple. Okay, so R is a 52 in the hex column, and an E is it's a lowercase e, so I need to jump over here. Yeah, it's a 65. And then a D is one up from that, right? One less, 64. Can I type? And then a space is a what? A space is a 20. It's punctuation. And then the apple, the A, 41. What's a P? Lowercase p is a 70. 2 70s. And an L is a 6C. And then lastly, the E is a 65. Okay. Now, is that all that it is, really? Well, there needs to be some indication of the end of the data. And so sometimes the end of the data is marked with 0, 0, just so that we know where the end of the string is, right? We know where to stop. That's one way to do it. What if we save the word red apple hit by the enter key as a text file? Well, if we look it up, there are some extra characters down here. Carriage return and line feed. So you might see a D followed by an A stored out there. Actually, a 0D and a 0A, right? Because if we were expressing these as pairs of hex digits. So DOS, the disk operating system, you know, what Bill Gates invented, you know, in the 70s, and we took it from somebody else anyways, decided that every line of text would be ended by a 0D, 0A. And Unix, the guys who invented, you know, the incredibly popular Unix operating system, decided that the end of a line of text was just a 0A, and so you would leave the 0D off. So it's very possible that you might edit a text document in Notepad, and it would look like garbage. It would look like it was all strung together, right, without any breaks. And that's because it's expecting 0D, 0As to terminate each line, whereas, you know, if you edit it with another editor that wasn't programmed to that specification, then it would treat just the lone 0A as a line feed. Anyways, let's go and do some ASCII to hex. At least do this I love Java. So kind of tuck that to the side and bring up ASCII-table.com in another window. And go ahead and convert that sentence, I love Java. Or skip that one and do your first name. It's short, right? It's far shorter. And turn those into hexadecimal values. When you're ready to check your work, go to this website, hexed.it. I'll show you how to use it in a minute, though. Some people are still typing. That should be. Which one you wind up doing? Oh, you're doing both of them? Or, okay.
Oh, you wanted an, I forgot. Okay.
No, we don't have to do both. Whichever. Unfortunately, I probably didn't leave enough space in this one to support the entire string, right? You'll probably run out of space. So you can make the column wider, or you can let it go ahead and expand the column, whatever, I don't care. So if somebody did I love Java, just for funsies, read off the digits to me. Who did I love Java? All right. Daniel, how about you read off the digits to me?
49
49
20
30
No,
wait 49
20
20
6C
6E
no 6C
C, thanks,
6F
6F
76
76
65
65
20
20
4A
4A
61
61
76
76 and then the exclamation point.
no 61
You need another A for the job.
Where did I goof?
you left out the last A
Oh, okay. So what is an A?
7.6,
7.6.
and then 6.1.
Okay. Yeah. Okay, 7.6.6.1. Got it.
No,
And then
you
21.
misplaced. The 6.1 goes there too.
There's two 6.1s in Java.
Yeah,
You're-
4A 6.1, 7.6.6.1,
4A 6.1. 7.6.6.1.
6.1.
Then 2.1.
All right. Thank you.
2.1, not 3.1.
2.1. Okay. All right. And then if I spaced them out with spaces between it to make it easier to read, that'd be better off.
That's what I did.
Okay. And then going in reverse, you just do the same thing, except you look up the hex values and you go to the ASCII values. I want to show you the website that I just mentioned called hexed.it. So, hexed.it. Go ahead and go to that site. It's short for Hex Editor. A Hex Editor is something that will let you modify a file by looking at the hex contents of it. And what you can do is, in this column, you can type in text, and it'll show you the ASCII representation of it. So for example, I love Java, ! Like that. Or if you have a series of hexadecimal characters, it'll show you the ASCII representation of them. 65, 66, 67, 68, 60, whatever, right? So I'm typing in hexadecimal characters and it's showing the ASCII representation over here. If you open up a Word document and expect to be able to understand what it looks like with a hex editor, you'll be disappointed. But you can open text files. So where it says open file, if I can go and find a file that I've created in the past, well, I guess that C++ directory no longer exists. I seem to have wiped out a lot of my data. There's something called boilerplate c.txt. You C++ guys will recognize this as soon as I open it, # include IOStream or whatever. This is the text file, and this is how it is saved in memory and in storage on your disk. So # is a 23 and a 69 and so on. Okay, I have talked about 10 minutes longer on this than I really intended to, because I wanted us to do a Java app. Did we do any Java last?
No.
I didn't think so. Alrighty, we can't let a whole week go by without doing Java, even if we only do 5 minutes worth of it. Go ahead and save your document. I don't care if you got it done or not. And upload it into the homework. You'll get full credit for it. But what I want us to do now is to fire up NetBeans. So I'm going to type in NetBeans down in the search bar. Oh, what do you know? Error message. Wonder if y'all are getting this.
Yep.
I guess just choose yes, default version, whatever that was, all right. Yeah, something subtly changed over the break, it seems like, because the C++ students, most of them are now having to relocate their projects directory. And what's odd is that it doesn't look like my machine changed. It's got all my files from the past semester, so I don't know why that's the case. Anyways. All right, so when you load NetBeans, what you're not going to do is just do a file new and create a Java file. Instead, you're going to create a project, and inside that project is going to be the Java file. You C++ guys will be familiar with that. You Python folks were probably not creating projects. If you were using idle, it didn't support that idea. So I'm going to do File, New Project. Click Next.
So is the Java application.
Yeah, so as far as the name is concerned, we could just call it Lecture B. Take a gander at where it's saving it. If we were going to ask you to upload it, Mine is being saved in my documents directory. So I'm going to click Finish. I had this check mark. I shouldn't have, let me bring that back up.
It automatically creates a
Yeah, if you have this checked, which I recommend that you do, it will create a main class for you, which is a lot of boilerplate. It saves you from typing. There are times when you're going to want to create a project without creating a main class. All right, so there is our Java class. We already have a program here. Doesn't do anything. Now when the Java runtime engine tries to run the application, it has to have a hook into the application in order to run. It has to have a main function, a main method to know where to start executing its code. And that's what we would do. That's where we would put. We need to put it right here where it says code application logic here. So why not? What are we going to make this do? Well, why don't we create a variable with our name? So we're going to use a string data type. We're going to give it a variable name. String name is equal to Bobby Roberts. Whatever. And now we're going to print that out. I need to increase the font size if I need to. If I can, quickly enough. All right, now let's print out the name. System, and it's okay that you don't know what I'm typing. We haven't even hit any of the PowerPoints yet. I just want us to have some hands-on experience before we walk out of here today. System, with a capital S, .out, notice that the editor's trying to help. Whenever I type a dot, you know, it lists all the subcomponents of that. So system.out.print, or is it right line? Excuse me, system.out. Oh, it was .print. Print ln, that's an L, not a 1, parentheses, quote, double quote, hello, comma, end quote, and then on the next line, or end quote, parentheses, semicolon, system.out.println. Don't put quotes there, though, because we want to print out the contents of that variable. So system.out.println, parentheses, name. So I'm going to run it. I'm going to save it with Control S. You don't have to save it. It'll offer to save it for you. And then I'm going to click the Run button, or the Run menu, and choose Build Project. And I'm going through more steps than you have to. You can just whale on that green arrow right there. But anyways, I built the project. I see this little churning bar down there, and then if I find my results, wherever the output window is, view, output. All right, there I see my output. It shows a whole bunch of stuff. Compiling source code to, copying, creating a file. It creates what's known as a jar file. And if you were going to run this from the command prompt, then you would need to execute this line of code here. But we don't have to do that because we can hit the green arrow and it'll run. And so it says, hello, comma, Bobby Roberts. It's kind of lame that those are on two separate lines. What if we want it on one line? A couple of ways we could do that. Let's just change this to print rather than print ln. If we take that ln off, it's not going to put a line feed at the end of it. It's not going to go to the next line like hitting carriage return on your keyboard. So if I run it again, I'm not going to do build because it runs automatically if I click the green button. Hello, Bobby Roberts. It put it all in one line. Now, if I wanted to, I could have made it print all in one line instead of with two statements. Here's what this would look like. System.out.print line, why not, quote, parentheses, quote, hi, comma, or let's make it say goodbye. Goodbye, because it's the last thing we're going to do. Goodbye, comma, space, end quote, plus the variable name, in parentheses, semicolon. Now in Python, you separated everything in a print statement by pluses. In some cases, with commas. In Java, you're not going to separate them with commas. You're going to separate them with pluses. Alrighty, so that's working. So I had a homework assignment queued up for y'all, and it's far too complicated for where we are right now. So I'm going to upload a different homework assignment, which is going to be this. Write a program that will display a haiku, a limerick. You know what a limerick is. There once was a man from Ireland who blah 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 blah, or part of a song using system.out.println. Now, a limerick is like 6 lines long, so you're going to have 6 print statements. A haiku, I believe, is 5, so you're going to have 5 print statements. However many lines, print lines you're going to need in order to print out, the lyrics to, whatever your favorite Lady Gaga song is or whatever. So that'll be your homework, and I'll make a Dropbox for it with instructions for that and upload it.
Since we did the hex to ASCII in class, are we saving this? Or?
Go ahead and upload that worksheet back into that homework directory.
Yeah.
And everybody will get credit for it. I don't care if you finished it or not. So go ahead and put your hexadecimal, your hex ASCII one into homework 1. Homework 2 is going to be changed to something else. If you're feeling totally ambitious because you've been, a Java programmer in the past, feel free to go ahead and do it.
Because I don't know where to go after the beginning.
Yeah. Okay, so let me stop the recorder, and then I will walk around and make sure everybody gets their files uploaded.